Okay, this is the last part on the topic on work, and this concerns work in pumping a fluid out of the tank that is going to pass through, or it's going to be on top of the tank. Okay, now this is another useful example of the application of integration, and this concerns computing work of uh, in pumping fluids out of the tank, which is often illustrated in the context of emptying a storage tank by pumping the fluid out the tank. Now, this situation is very different than our previous examples, where the forces involved here are not, or rather are constant. Now, after all, the force required to move 1 cubic foot of water about, let's say, 62.4 pounds, this is the density of water, is the same regardless of its location in the tank. So in this case, the force applied is constant class. So in Hooke's law, the force applied is variable, but in the case of pumping of fluids, the force that is to be placed in the equation for work is constant. What is going to vary here is the distance in which this particular work is going to traverse, or the displacement of a particular section of fluid, or we call it differential volume of fluid. So that distance is going to vary. So the force itself is constant. It's the distance that is going to vary. Now, the water, in this case, that is closer to the top of the tank, of course, will require lesser work because the distance that you need to travel to be pumped out on top of the tank is lesser compared to the fluid or the water, for example, at the bottom of the tank, which is of a farther distance than the layer of fluid on top of the tank. So let me proceed to the next slide. Feel free to ask questions if it's not clear. Now, in this example, I started with this example in the other classes as well. I decided to place it here in example 5 because our differential volume of liquid is constant. Now, in here, you're given a cylindrical tank. So I hope everybody is familiar with what is a cylinder, what's the shape of a cylinder. And this cylinder has a radius of 10 feet and a height of 30 feet. And it is filled with water. Now, mentioned already in the introduction that this water weighs approximately 62.4 pounds per cubic feet. That's the volume of water. So this particular constant is the density of water. Compute the amount of work performed by pumping the water up to 0.5 feet above the top of the tank. So as you can see here, this is the height of our tank and it's filled with water. Now, the goal is to have all this water pumped out at a distance of 5 feet above this particular tank. So you notice the total distance now from the bottom to the top, in which your differential volume, this is the differential volume of water, in which you're going to travel is 35, because the height of the tank plus the 5 feet above it, that would make it 35 for the total distance in which its differential volume of water is going to travel. Now, you are required in this case to compute the work performed by pumping the water up to 0.5 feet above the top of the tank. Okay, so I've read that already. Now, this particular colored portion, blue colored portion, is what I'm referring to as the differential volume of water, or the differential volume of fluid, and it's going to be, let's say in this particular illustration, it's going to be lifted up, or it's going to travel a distance of, if the entire height here from the bottom of the tank is 35, and we set this one as y from here to here, then this remaining distance in which this differential volume of water is going to travel is the entire height, which is 35, minus the y, or the yi. Okay? Of course, the distance, if we refer to the differential volume in here below, that would be longer, or that would be farther from the top of the tank, or that would be farther from 5 feet above the tank, because we are here at this particular location. And as such, during the introduction, it says that the force is constant, it's fixed. However, it's the distance that is varied. Now, as for the solution of the problem, we will refer to this figure from time to time. That way you will understand. And feel free to ask questions if you think you cannot follow. Now, consider the work W, or the W sub I, of pumping only the water residing in the ith subinterval as illustrated in the figure. This is the ith subinterval. This is the subinterval, the differential volume, because we represent this height from 0 up to this point as y sub I. Okay, so that's the distance of this differential volume from the bottom of the tank, and it's being referred to in here in the discussion as the ith subinterval. The force required to move this water is equal to its weight, which we calculate as the volume times the density. Now, your physics taught you that when we speak of density, it's equal to the mass over the volume. Now, if we cross multiply in here, you will have an expression which is mass equal to the product of the density times the volume. This mass in here is the force after it's being multiplied to the gravitational constant G. So it's converted to the force, which is actually mg if we're using SI set of units. If the units that the problem is giving you is English, then this would even be, so I will just continue here for English, it would be mg over g sub c. Now your physics taught you that this g, the gravitational constant, if it's SI, will simply be 9.8 meters per second squared, and it's able to convert the mass that we get out of multiplying the density and the volume to Newton. So the corresponding unit now of the force in here, if it's SI, will be Newton. Okay, just a short review. Now the other formula that you have here on the right is still actually similar to this one. However, this is for the English set of units, wherein this G is in 32.2 feet per second squared. Now, simply multiplying your mass in pounds, or pound mass specifically, to 32.2 feet per second squared does not convert it to pound force. It needs this G sub C, this conversion. Now, the conversion G sub C depends on, I think, if I'm not mistaken, this is 32.2 also. Okay, 32.2, and it will convert your pound mass feet per second squared to pound force. So that's the purpose. Okay. Now in this case, since we have here the mass in pound mass times this G, which is in feet per second squared, so we need to have the unit of this 32.2 set in this manner. That way you will have a corresponding unit of pound force. In this case, class, let me just erase. If it's going to be division, then in here in the numerator, you will have the pound mass. So you will have here pound mass, and you will have here feet per second squared, and you will have here pound force. Now you have converted the unit pound mass feet per second squared to pound force. So I have interchanged the units, by the way, so that's a mistake there, because there's a need for you to convert the pound mass feet per second squared to pound force. So I have interchanged the sets of units here. But anyhow, I know that you have that you can recall this easily because you have encountered this already in your physics. Now this G sub C, to be exact, is 32.2174 to up to the last 4 digits here on the right. That is a fixed value, class. It's a fixed constant that is used for conversion. However, this G, as for this G in here, the value I placed here, which is 32.2, is just an example. You know that the G changes in terms of location. So your G, if you are in, let's say, in the United States of America, will be different than your G if you are in the equator or something like that. So it changes. So this one varies. But most of the time, class, it's just being assumed that the G, since its variation is not really that big, this G is just the same as the G sub C. So automatically, if you multiply the mass in pound mass to the G over G sub C, it would just be still the same as the original value in pound mass. What I'm trying to say is if you assume that the G and the G sub C more or less will be the same, your mass, pound mass is just the same as the pound force quantity. So if you have 10 pound mass for the mass, if converted to force, that would also be 10 pound force because we have assumed that the G and the G sub C are just the same or equal. Now, cumbersome, it may be for, let's say, when we talk about English units, but that's just the way it is. Now, if it's SI, it's okay because we don't need to have, we don't need to use the G sub C. We just need to multiply the mass that is in kilograms to the G, the gravitational constant, which is 9.8 meters per second squared. So I will go back in here now so that you will understand. I just had here a little review of what you've learned in your physics because it's being mentioned in here. So going back to this statement again, the force required to move this water is equal to the weight, which we calculate as the volume times density. So take note, it says here that the force already, the force is equal to the product of the volume times the density. If you look at it, density times the volume is just still mass. However, in this problem, since we're dealing with English units, this is what I mentioned a while ago, there's an assumption that the G for the particular location where this tank is located and the G sub C are just equal. So in this case, automatic. The mass that is given in pound mass is converted already to pound force by simply multiplying volume and density. Okay, I hope you get it. So this is already our force in this case, in the problem. The force is equal to the product of the density times the volume. Now moving on, the volume of the water in the sub-interval in this particular location here is equal to 10 squared pi times the delta yi. Now you may wonder where is this 10 squared pi? Now we know that for this particular disk or for this particular very shallow cylinder, the volume of the water is equal to the area, the circular area of the face in here times its thickness. Now the thickness is the delta yi and the area of the circular section is the product of the square of the radius and pi. So that is why you have your pi times 10 squared because the problem says that your radius is 10 feet. And you're going to multiply it, of course, with the height. Okay? Now, you've learned also in your solid mensuration that in terms of the volume of the cylinder, it's the product of the area of the circular face times its height. So this is just to be viewed as a very shallow cylinder, or it's a disk, and as such, its volume will be computed in this manner. Never mind this, there has been a double pasting here of the particular quantity that you see here. Anyway, they're just the same. So the volume is of this differential fluid element is 100 pi delta yi. Now, its density is 62.4. So there's a double pasting here. So if you multiply the volume with the density, as you could see here, that will be now the force, which is the mass. Thus, the required force is equal to 6,240. This is after you have multiplied the 62.4 by the 100 here, times the pi, times the delta yi. This is already the expression for the force. So if you're going to write the work required to empty out all the water in this tank to a 0.5 meters above the top of the tank, you have here the expression for the force. This one, split lang sila. So this is the force together with this. 6,240 pi dy. The dy corresponds to the delta yi here times the distance. Because we know that when we speak of work, it's the product of the force times the displacement or the distance. So you have the force here together with the dy, and this is the displacement. A while ago, I explained why you have 35 minus y for the displacement, and I will explain again so that it will be clearer. So for this differential volume of fluid, the one that this one, the blue part, if this particular differential volume of fluid is said to be located on this ith interval, in which the distance is y from the bottom, then the distance that it will travel to be pumped up to this level is 35 minus y, because this entire thing is 35. So this is your displacement. So the force times the displacement is the required amount of work to empty the tank. So all you have to do is do your mathematics. Notice that your limit here is from 0 to 30. Because in terms of the dy, this differential height, it's only from 0 to 30. The height of the liquid inside the tank is only until 30, not 35. Because 35 is just the total distance in which this differential volume of fluid is to be traveling anywhere there, if the purpose is to empty the tank. So you have 0 to 30, okay, for the y, for the delta yi, the thickness of this shallow cylinder or the thickness of this disc. And this will be the corresponding work done in pumping the fluid or the work done in emptying the tank. Properly, class, if you're going to write this, it should be 1.176 times 10 raised to 7 foot-pound force. Now, when I remember my physics then, my teacher would really require us to specify what is the pound unit if it's being used in our calculation, because we have 2 pound units. It's the pound mass and the pound force. So the two has to be specific. So in this case, it should be foot-pound force. Any question for now? Any clarification on what I have discussed? So it's the volume times the density, which is equivalent to the force. Once you have the force, you still need to multiply it with the displacement to get the work done. So it's the same fundamental principle about work. The force applied in the direction of the displacement. Yes, JB.
To clarify, what is V sub I gonna miss? In
Okay, the V sub I, okay. This V sub I is the volume, this differential volume of element, it's V sub I. So you have the volume of this differential element is equal to the area of the circular cross-section and its thickness. The area of the circular cross-section is pi r squared. The thickness, so since it depends on what is the thickness that you are referring, that you are using, so that's the delta yi, equivalent to the dy, the differential dy in calculus. Now, the entire expression here is now actually the volume times the density. The 6,240 pi dy is the volume, which is pi r squared dy times the density, which is 62.4. So that is why you see this. This is your force, and this is your displacement. The force needs the volume together with the density. They need to be multiplied, that way you have the force. Did you get the explanation?
yes, miss. Thank you.
Any question? Okay. So, no more questions already? Okay. Here are my markings, and we'll proceed to the next. In here, we have a different solid. So your tank here is not uniform in cross-section because in the case of the cylindrical tank, wherever you are here, your cross-section is that of a circle. Okay? They only differ on the thickness of the cross-section, the representation of the thickness of that particular cross-section. It's uniform. And any point in here, or it's as referred to in here, in any sub-interval in here, it's uniform. It's in this shape. But in this example, it's not uniform anymore. Because if you notice, if you're in here, in this part, on the top part of this conical tank, your circular cross-section will have a bigger area compared to this particular blue section here, colored section in here that is indicated. So in this case, your cross-section, the area of your cross-section is changing. So how are you going to solve such a problem when the area of the cross-section is changing? So we're just going to go through this piece by piece. So a conical water tank has its top at ground level and its base 10 feet below the ground. We can imagine this conical tank embedded or submerged on the ground. So this is ground level in here. 0 is ground level. So the tank has the shape of the cone. So you could see that if we'll assign 0 in the Cartesian plane, the top of the tank, since it is below the ground, its tip is in here, having a coordinate of -10 in terms of the y, okay, because it's below the ground. And we have assigned 0 for the ground level. Now, the radius of the cone at ground level is 2 feet. So you can see it's being indicated in here. It is filled with water weighing 62.4 pounds per cubic feet. So same density as sample problem 5. And it is to be emptied by pumping the water to a spigot 3 feet above the ground. So the goal is all the water in this conical shaped tank will be pumped out, passing to the top of the tank 5 feet above the ground, or above the tank itself, or top of the tank itself. So we're going to pump it up 5 feet above ground level. Find the total amount of work performed in emptying the tank. So what's the total amount of work performed in emptying this tank? Okay, so our illustration is this one. So you have a conical tank, and this is I'll just annotate here, the distance of this particular differential volume from the bottom is 5. Okay, you can see here it's 5. So if we have 3 in here, since all the water inside this tank will be emptied on a location 3 feet above the top of the tank. So you can see now that the remaining distance of this differential volume of water, the remaining distance that it will have to travel to reach the spigot is 3 minus 5, because we have assigned this already as y. You could see the y in here already, but I just wrote it in here so that you can easily grasp this representation of 3 minus y. This one is y, and this one is, the entire distance is 3 minus y. Oh, sorry, by the way, 3 minus y, that's correct. So the same representation as this one that you can see. It's also y, not yi. Okay, now, as to the solution, let y equal to 0 represent the ground level, and hence y equal to -10 represents the bottom of the tank. So this is -10 for the y here. So I place this one in terms of its y coordinate. This would be -10. And for the top of the tank, let's say at this point here, you will have, in terms of the y coordinate only, this will be your 0. I did not place anything here on the x. We'll just go there one at a time. Okay, so -10 at this point for the y, and you have here 0 at this particular point in here. It's indicated on the illustration. Now, the actual height of the water in this case does not matter. We are concerned with the distance the water travels. So the distance the water travels, as indicated in here, for this differential volume of water is 3 minus y, because we have represented this as y. Okay, measured from in here, because that's how we measure it in the Cartesian plane. We start at 0 point. So 3 minus y will be this distance. The entire distance is 3 minus y, so that would be this one. The figure shows an element, a cross-sectional circle. So this is also a circle. The radius of this circle is variable depending on the y. So this your circle in here, as I have mentioned a while ago, will have a bigger radius than the circle that you have in here, even more so with the circle that we have in here. The radius will be varying. It's not fixed. Now, when y is equal to negative 10, the circle has a radius of 0. Okay, you have noticed in here. So meaning, in this case, class, you will put your y-axis, yes, your vertical axis, your y-axis here on the center. Then at this point, which is set to have a y of negative 10, since it's in here, right on the axis, its x is 0. So when y is equal to negative 10, the radius is 0. When y is 0, the radius is equal to 2. So you could see in here, if this is 0, the radius from, if measured from this distance of our vertical axis to here, will be 2. So in this case now, this will be 2. So the points, these 2 points, have these 2 very important sets of coordinates, 0 and negative 10 at the tip of the conical tank, and 2, 0 for this particular point at the center of the tank, on ground level. Okay, it's 2 for the x and it's 0 for the y. So it says here, the circle has a radius 0, then when y is equal to 0, the circle has a radius of 2. And by the way, let me just erase this part. If it's the radius which is 2 and the y which is 0, the point that we are referring to is this point in here, not the one at the center. If we have placed our vertical axis in here, everything in here will be 0. This will have 0, 0 as the coordinate. But if you're referring to this point in here, this will have 2, 0. Okay, I'll erase this part so you will not get mixed up. Okay, in terms of the discussion on the radius, this point on the tip of the conical tank has the coordinates 0 for the r and negative 10 in terms of here, the y location, negative 10. As for this point, you will have 2 for the x and 0 for the y, because it's in here right on the ground, which we have set to 0. I will erase again here so you will not be confused as to the representation. So the 2 points that we have now is this, the 2, 0 and the 0, negative 10. Now before I proceed, do you follow? Do you understand? Okay. So maybe you're silent, you're still processing.
Yes, miss.
Your silence, or it's clear. So anyway, if you don't follow, if you can't follow, then just let me know. Now we proceed here on the next explanation. Okay, the figure shows an element, a cross-section circle, and we have reached until this particular explanation here regarding the location of the radius, the varying radius of our circular cross-section. These 2 points now, if you're going to write the coordinate system, is negative 10, 0, and 0, 2. Allow us to find the equation of the line that gives the radius of the cross-sectional circle which is, so you could see here, the radius, which is y, as a function of y rather, is equal to 1/5 y plus 2. Now, using these two sets of coordinates, the -2, 0 and 0, 2, you were able to get this formula for the radius, the varying radius as a function of y. You could see it's an equation of a line which has the slope equal to 1/5, and you have here 2. Now, if I will ask, if somebody can tell me and could guess how was 1/5 as the slope calculated, and how was the 2 here arrived at? How was this take calculated, number 2? You are going to base your answers to these two sets of coordinates, -10, 0, and 0, 2. -10, 0, and 0, 2. Now, can somebody explain to me how the 1/5 came about? If this is compared to an equation of the line, just use a different font so you will follow through. This is your y, this is your n, this is your x, and this is your b. So the question is, how was the slope calculated in this case? How was it arrived at? 1/5. So you could see here, radius is equal to 1/5 y plus 2. Vincent is raising his hand. I have, yes, Vincent.
For the 1/5, miss, I think it is, the formula used is y2 minus y1 over x2 minus x1, miss.
Now, actually, Vincent is correct. So if you take it from the set of coordinates that you have, it's actually interchange. You notice na interchange siya. Our coordinates here is 0, -10, and 2, 0. The way it's written here, it's the other way around. You have -10, 0, and 0, 2. Now, Vincent probably just took the, or used the formula of the slope. I'll use the green font, the green color. You have m equal to y2 minus y1 over x2 minus x1. Now, based on our coordinate system, these are now the y's. So you can either have this minus this or this minus this, as long as you follow the order of subtraction. So you can have 0 minus 2, and you'll have here -10 minus 0. So in this case, you have -2 over -10, which will give you 1/5. So Vincent is right when he said that the slope was taken from the, or the 1/5 was taken from the formula of the slope, which is y2 minus y1, x2 minus x1. Now, it's taken from this 2. The form is taken from here. The two sets of coordinates are taken in here, only that they were interchanged. So I have a question now. It would be easy to follow through the slope based on these two sets of coordinates because you just have to follow the formula. Now, why was it interchanged? Why the 0, -10 in here interchange to -10, 0, and you will have 0, 2. Why not stick to 0, -10, 0, -10 in here, and then in this case you have 2, 0. Why need to interchange it in this form and then solve the slope using the formula of the difference in y over the difference in x coordinates? Anyone? Why interchange? Oh, amo ni siyang original taho. And it's easy to follow because we're using here xy. This is xy also in terms of these 2 points in here. Why was it interchanged in this case? You have -10, 0 now, and you have 0, 2. Anyone? Nga aging sulit siya, nga hindi amo ni. Actually, if you stick to this set of coordinates in here, this one, then the slope that you will be getting will not be 1/5. because that would be then negative 10 minus 0 over 0 minus 2. And it will not give you 1/5, it will give you 5. So the answer is different. So my question is, why interchange? Would somebody have the answer, or would somebody know the explanation behind why interchange the two? Hmm? Okay, it's JB always that is participating. Let's see somebody. Let's hear from somebody who is probably just shy to express his or her thoughts. Can I ask Keisha? Would you have any idea, Keisha, why interchange the coordinate systems that we have set in here? Keisha, would you know? Or anybody here? Floyd, would you know? Jason,
I'm not sure, Miss.
Floyd, what do you think is the reason behind? Just guess. Probably your guess is the most intelligent guess that I have heard so far. Predicate so that there's slopeness. Yes, whether you use this set of coordinates actually or the original, you will still be able to solve the slope, but you will be getting different values. So my question is, use our vernacular language, nga aging suli, nga hindi na lang 0, negative 10, and 2, 0, nga suliun siya, kag dason, after they were interchanged, that's the time that the slope was determined. Why? Hmm? Sige, so I will explain to you. Please listen so you will understand. The reason why, class, the original coordinate systems that were given, so you can see that these were the two sets of coordinates mentioned here in terms of how the radius varies in terms of the location of the point, the y that is. It's because it is this time the radius that is dependent on the y, not that the y depends on the x. The way you were taught in algebra, in the coordinate system x and y, this variable y depends on x. Meaning, you will only know the value of y if x is known. Now, in this case of the problem on the conical water tank, it's the other way around. The radius varies. It's now the r. It's the x that varies, and it's dependent on the y, the location here on the vertical axis. So that's the purpose of interchanging 0, negative 10 to negative 10, 0, or writing 0, negative 10 to negative 10, 0. It's the same thing in here. Writing 2, 0 to 0, 2. We interchange because the radius is dependent on the y, not that the y is dependent on the x, as our usual convention. Okay, when we write even equation, we say y of x equal to, let's say, 2x plus 10, telling us that y is a function of x, so meaning it's dependent on x. In this case, as it is written here, you could see your r, the radius, is dependent on y. So you have to interchange the original set of coordinates written here. We will now place the radius after the radius location after we have specified the vertical coordinates, which is the negative 10 and 0 in this case. Okay, so i-interchange din siya. Kag dapat naintindihan nga i-interchange. Because if not, your answer will be wrong because you'll be getting a, shall I say, a value of slope which is 5, 1/5, and in the other one that would be 10 because that would be 5 rather, divided by 2. So it could be 1/5 for the other, in this case the correct one, or it could be 5. Now, you already know the slope of the equation of the radius in terms of the y. location, the displacement, or the height of the water inside the tank, because they are both represented by y. Now, what about the 2? Where do you think the 2 came from?
Miss, is it the y-intercept?
It's the y-intercept. So in this case, when we speak of the y-intercept, it's the point on the y-axis where your particular line crosses, right? The point on the y-axis where your particular point crosses. So what is the x for that particular point? The y-intercept. I'll use another uh, analytic geometry review. If this is your Cartesian plane, and I have this line, this is the y-intercept, right? That's the y-intercept, the point on the y-axis where your line is crossing. So in this case, how did you get the 2? How did you get the 2? Anybody? Why is it 2 in here? Well, you could see it's 2. How did it came about? Okay, somebody wrote on the chat box. Radius. What about the radius? There's Feather Gay. What about the radius? What about the radius? Paano nakuha ini siya ang 2? Silin nyo, kung amo ni equations ng line, it's the y-intercept. True. If it's the y-intercept, we look into our analytic geom. We go back to our analytic geom. This is the y-intercept of this line, the one that I have placed there in red. It crossed the vertical axis on that point. I'm giving you already the guide there. Why then 2 in the case of this problem? Why 2? Why gid? Why gid may kaget? Sara na siya o. So nga at 2 ang gimbutang ta. Sige ah. Si Miss Ali explain ha. Okay, mayari be. Because 2 is in the y-axis, Miss. Because 2 is in the y-axis, Miss. And x is 0. Okay. That's correct. Okay. Probably just stated differently, but I think I know what you mean. So that's correct. So this is it. You see this point? This is the coordinates of this point. Isn't this x and y in our representation? Now, when you look at this particular point in here, the y-intercept, since it crosses the y-axis, its x-coordinate is 0. And it will have a certain value on the y. Now, in our 2-point systems in here, this is the corresponding point. 0, 2. You look for the points in here in which the x is 0. What is its y? That's 2. So then that is the y-intercept. You get it? This is the x, which is 0. All y-intercepts, all points representing y-intercepts will have a coordinate of 0 for the x. Then it depends on which location on the y-axis it rests on. I'm referring to the point. So in this case, it's 2. So then that's the reason you have 2. Because I'm using the set of coordinates. When x is 0, y is 2. So that's it. Now, what about Miss Ali if I use this point? Pwede mo din siya i-use. In here, this is the x and this is the y. In our in our problem, in our, not problem, in our equation, our x is negative 10. So you place here negative 10. Negative 10 divided by 2 is equal to b. What about this r, which is the y0? So you will still be getting the same answer, whichever solution you substitute. Okay, I'll do that. I'll substitute. I'll use this point this time. This is the x and this is the y. So the y is the r, so it's 0 equal to 1/5. Now the y is negative 10. We have b. So b is equal to 2. So it's the same thing. Do you get it? Your y, the r is 0. Your x is negative 10. So negative 10 divided by 2, rather divided by 5 is negative 2. You transfer it here, that will be positive. So either way should you look at it. Either you use this point or this point, you will still be getting the same y-intercept. But this is the easy route, class. You just look for a set of coordinates in which x is equal to 0. The paired coordinate is already the y-intercept because this tells you that this point rests on the y-axis. All points here have an x coordinate of 0. So then your y-intercept is 2. But if you use this set of coordinates, okay malang yapon substitute mo lang da sa imo equation. You have b as the unknown. Your y is 0, your x is negative 10. And you'll be getting a b, which is 2. So the same thing. Do you get it? Do you understand before I proceed to the ones written below, the explanation?
Yes, ma'am.
What about the others? So ang Premi ang discuss together with me, is engaged with me, is just probably 2-3 persons. So I hope those that are silent can follow too. I don't mind having to repeat areas here if it's not clear to you, as long as you understand. Okay, now the figure shows an element, so that's the one that I have read a while ago. So this is the element that is being referred to. Okay, now we proceed with the next thing there. So the radius now is equal to 1/5 y plus 2. Hence, the volume of the water at this height is equal to, so the radius, remember this is the equation of the radius that varies. So 1/5 y plus 2. If we have this cross section as that of a circle, then this must be pi r squared for the area of this circular cross section. So you have pi times the square of 1/5 y plus 2 squared. Then the thickness of this differential volume of element is dy. Okay? Area of the cross-section is pi times the quantity 1/5 y plus 2 squared, and then the thickness, which is dy. Now, dy represents a very small height of the differential element. So the force required to move the water, the same thing with sample problem number 1, since we already have the volume, we just need to multiply by the density. So the density is 62.4 times the volume, that will give you the force. Now that is only the force. What about the displacement of any particular differential volume of water here? The displacement will be 3, the entire height. From here to here, it's 3. So in terms of our representation, it's 3 minus y. This is the y. The, shall I say, the location of this differential volume of elements. So it's y here. So 3 minus y will give you this particular distance. Amo na lang ni ang iya nga i-cover nga displacement. Okay? Then the distance to water at height y travels is given by 3 minus y. Thus the total work done in pumping the water from the tank is this one. So your force, this is right. So this is your force class, the 62.4 pi 1/5 y plus 2 squared, and this. This is your force together with this. That's your force expression. The 3 minus y is the displacement. So that still works. Now notice the limits of integration. Since the elevation is negative 10 here at the bottom going up, which is 0, so you can see here, it's negative 10 to 0. Okay? You do your expansion here, you do your mathematics, you do your power rule, you substitute the limits, you will have the work. The same work or the same principle applied in sample problem number, what is that? Number 5. Any question? No more questions? Sige, class. I'll give you a breather, probably a 5-minute break. We'll have the last problem on this particular topic on pumping of fluids. Okay? I'll just have this pause. This one is the last of the problems on work. A little bit complicated, but I'll try to slice the problem, make it simple for you. If you're having problem understanding it, I will repeat the part, but just let me know. Okay, this concerns about the swimming pool. So a rectangular swimming pool. The rectangular swimming pool that is being referred to in here is the rectangular thing is its cross section. So it's in the shape of a triangle. Why is it a rectangle? Because its width is 20 feet and its length is 25 feet. I will just annotate so you will see what is meant by the width and the length. So that the 20 feet wide swimming pool is this. This is, if I'm going to draw it in here, this is more or less the swimming pool. Okay, this is the width that is being referred to. I just make it bigger so you will more or less have a clear picture. That's the width, and this is the length of our rectangular swimming pool. Rectangular in the sense that it's 20 by 25 feet in cross section. So that is why it's a rectangle. Now, the shallow end is 3 feet. This is referring to the shallow end, and the deep end is 6 feet. So if you look on the top, your cross-section is rectangular, but if you look on the side, this is the corresponding cross-section. So you will be actually having 2 different cross-sections on the side of our swimming pool. This rectangle on top and this trapezoid here below. Okay, but the rectangular thing that is being referred to in here in our problem itself is this space here, the top portion of the pool, and if you're going to look down, what you see is a rectangle through and through. This rectangle is constant. The rectangular cross-section is constant anywhere in, if you look at an our pool, anywhere it's a rectangle. Okay, now, where is it? It is to have its water, referring to the swimming pool, pumped out to a point 2 feet above the current top of the water. So if this is the top of the water, all of this water in our pools will be, will be pumped out 2 feet above this level. Now, if we take this particular cross-section on the side of our swimming pool written, have it written on the Cartesian plane, this is your x-axis and this is your y-axis. And this is the top level of the water inside or in our pool, then 2 feet above it would be this one. So this is the point. 2 feet above the surface of the water in our swimming pool. Okay, so you could see that for this particular trapezoidal portion, the points here on the sides that tells us the difference in the lengths of the 2 parallel sides are in terms of coordinates specified. So for this point here, you have 10, 0. This is 10 feet. And in terms of elevation is 0 from the bottom of the pool. Well, this particular point here is 15. How did it get 15? This is 10 feet. This is 25. So 25 minus 10, that would be 15. The elevation is 3. The entire thing is 6. If you subtract these 3 here, so this must be 3. Okay, so you see here 15 for the x and 3 for the y. Now, before I proceed, do you follow? So in terms of the representation of the points on the sides of our swimming pool, especially on the trapezoidal cross-section in which the length of the 2 parallel sides, the parallel sides that I'm referring to are these 2. Now, these are our parallel sides, are of course not equal. Okay, one has a length of 10, the other one has a length of 15. Now, the figure shows the pool oriented with the y-axis along with 2 differential elements, as the pool must be split into 2 different regions. So these are the 2 different regions of our pool, and these are the points. Okay? Now, if there aren't any question, I will proceed to the next slide. Okay, so there's none. I'll go to the next slide. The top region lies on the y-interval 3, 6, where the length of the differential element is 25. So 25, this is the length. The width is the 20 here, class, which I have drawn. So I will draw it here so you can easily visualize. So this is your 20. Okay. Something like that. So that's how it is. But we're just concerned with this one. So the top region lies on the y-interval 3 to 6. Why 3 to 6? Because this one is 3 and this one is 6 in terms of the location of the points with reference to the y-axis. Okay? The length is 25 feet. So this is 25 feet. The 25 feet is the original length that is written in the previous slide. I'll go back to that particular part later. Anyway, it was shown to you a few minutes ago. As the pool is 20 feet wide, the differential element represents a slice of water with the volume. So the volume of this water on the top portion is equal to 20 times 25. This space, the area of this space, the rectangle, is 20 times 25 times this differential element. So the differential element is dy. So I use the blue, so you will see what particular differential element I'm referring to. This one. So we'll get, if we will get a differential element on this section, the top section of the pool, so the volume of this differential element, if this is dy, will be 20 times 25 dy. Of course, the limits will be from 3 to 6 because we're referring on this section of our pool. So I'll just divide it in here so you will know. Okay? So this is the volume of the top region or section. The water is to be pumped up to a height of 2 feet above the surface of the water. So the height function or the displacement is 8 minus y. So from here, from the bottom of the pool up to the top, you have 8. 0 here, and then you have 8 here. At any particular section in here, let's say this one or this one, you will have y as the elevation of the water as measured from here. So if that y is subtracted from the 8, the total, then that's the distance traveled by this differential volume of water. Okay? Y, if this is y, for example, if this is y, location y, and this is the entire height, which is 8. So 8, the entire height, minus y will give you the distance that will be covered, or the distance in which this differential volume of water element will be displaced. 8 minus y. So that's the height function. The work done in pumping this top region of the water is, so you could see 500 is 20 times 25. So the 500 and the dy actually is the force. The force. and then it's multiplied here by the density. So ang density, since it is constant, it's just written outside. The density times the volume will give you the force. So since it's a constant, as I have said, it's written outside. The same thing with this 500, it could be written outside as well. The displacement is the 8 minus y. So this is the displacement. So since it's in the top region, we're determining the work in pumping out the water in this top region, then our limits of integration, you have to be very careful, would be 3 to 6. 3 to 6. Because it's the top region water that we are computing the work of in emptying that part. On the other end, on one end of the differential, the bottom region and this on the other side, on the other hand, is having the interval 0 to 3. Now, why is it 0 to 3? Because I'll place it in here. This is 0. This is 3. So your limits of integration at the bottom part of this particular side section of the pool will be from 0 to 3. The upper region or the upper part is 3 to 6. So you could see it in here. The bottom region lies in the y interval 0 to 3. And we need to compute the length of the differential element in this interval. The same with the conical tank example, in example 6. In the conical tank, our radius changes with elevation. In here, this one changes also with respect to elevation or y. Naga-change siya. May ara gamay, kung ara di sa dalo, may ara dako, kung ara na sa sababaw. Or it's nearing even this particular region here. So it does not, it is varying. It's not constant. So in this case, we need to have another equation that will express how will this length behave with respect to elevation. So meaning this length is dependent on the y. Okay? So one end of our differential element is at x equal to 0 and the other and is along the line segment joining the points 10, 0, and 53. Now you could see these are the 2 points that we have, and I have explained it a while ago how these 2 points got their coordinates. Now, the equation of this line, so here we go again, the equation of our line is y equal to 3/5, and you have here x minus 10. Now, if I will have this expanded, this would look like the equation of your line is 3/5 x minus 30 minus 5. So that would be 6. If you're going to have it expanded. So 30 divided by 5 is 6. Now, my question is, how did the 3/5 came about? So, paano ta nakuha ang 3/5? What was that? How was the 3/5? Or how did we get the 3/5 answer for the slope of of this line equation here? If we stick to the original equation, this is the original equation, and I just have simplified it in here. Paano nakuha ang 3/5? Your set of coordinates, I'll write it here ha. Your set of coordinates is 10, 0, and you have 15, 3. How was the slope determined? Same thing with what JV mentioned a while ago. Slope is delta y over delta x. So you can have this 3 minus 0 over 15 minus 10. So that's 3 over 5. Okay? That explains the 3/5 here. Now, how about this minus 10 here, which is equivalent to 6? Because it's 3 times 10 divided by 5. So negative 6. How did it came about? So the same thing. If your equation of the line now is y equal to 3/5 x plus b, you want to know this b. you just choose any of the points that you have in here. So this one is easier because your y is already 0. If you substitute for the point 10, 0, if you substitute it, you will have 0 equal to 3/5 times 10 plus b. That's the reason why you have here negative 10. Because if you transfer it here on the other side, you will have negative 30 over 5. And b is equal to negative 6, which is the same as this one. Okay? So now you have an equation of the length of this differential volume that is varying. Now, how do we then write the work expression for the lower region of our rectangular swimming pool? Okay, we will proceed here. So the equation of this line is y equal to 3x, or rather 3 over 5 times the quantity x minus 10. As we will be integrating with respect to y, we rewrite the equation as. So notice, this particular equation is y as a function of x. Now it says here you will be integrating with respect to y. Now you may ask, Miss Ali, why is it saying that you will be integrating with respect to y? Because of this. The height of your differential volume of the element is dy. So, hindi pwede na x ang imo variable, ang imo nga differential in terms of y. So, from this particular equation, this one, your y equal to 3 over 5x minus 6, you solve for an equation of x in terms of y. So, what do I mean? So, you transfer y plus 6 is equal to 3/5 x. You transfer this one here, so you will have, I'll place it here, 5 times the quantity y plus 6 is equal to 3x. Then, diripagit. So, x is equal to 5 over 3y. And then, you have here 30 divided by 3 plus 10. So, your equation now of x in terms of y would be this. X is equal to 5 over 3 times y plus 10. Again, y express the equation in terms of y, not in terms of x. It's because of our height of our differential volume, which is dy. So it has to be now x in terms of y. So this is your x in terms of y equation. Okay? But we're not yet done in terms of this particular volume for the lower region. So we just have determined so far the length. The length times the width times the height. Okay? But before I erase everything, do you have any question? This is actually your varying length. So in terms of work, you have actually the length times the width. So the width is 20. The length is 5 over 3y plus 10. And then length times width times the height, which is dy. So take note of this. We will go to the next slide. I will erase this part. You have to check if this is the expression. Your dy in the lower region will be from 0 to 3. So you have here 0 to 3. Just like in the upper region or in the top region, you have assigned it 3 to 6. Okay? So 20 times 5 over 3y plus 10. Any question? Okay, I'll clear my marking so we can proceed to the next part. Okay, so again, as the pool is 20 feet wide, so this differential element represents a thin slice of water with volume 5 over 3y plus 10 times 20. Okay, that's the volume. By the way, I missed to write the 62.4, which is the density. To convert the volume into force. Okay, so 62.4 times this particular volume, this is your volume, that would give you your force, and this is the displacement. It's still 8 minus y. Why it's still 8 minus y, Miss Ali? Because it's from here to here. The water in this section will be, shall I say, dispensed, pumped out on top of the swimming pool 2 feet above the surface of the water level. So it's still 8 minus y. So you have now the limits of 0 to 3. So this particular work is for the bottom region. For the top region, it was computed to be 299,520. So you add the 2. This will be the total work done in emptying our rectangular swimming pool. Now, there's a very important note that I place in here. Notice how the emptying of the bottom of the pool performs almost as much work as emptying the top. So this is the bottom work, and this is the work in emptying the bottom, and this is the work in emptying the top. It's still bigger because, of course, the displacement here is longer, or shall I say, yes, the displacement will be longer because ara siya sa dalom, diri hindi. But however, since in terms of the weight, the top portion travels a shorter distance but has more water. Why is it has more water? Because of this section here. This section is bigger. So though it will travel a shorter distance to reach this height of 2 feet above the surface of the water, you'll have a heavier water, as I'm about to say a while ago, because in here your cross section is bigger. So your water, the force is larger compared to the force in here at the bottom, as explained in here. The top portion travels a shorter distance but has more water. In the end, this extra water produces also more work. But still, work in emptying the tank will be more in the bottom region. So more work is required in taking out the water in the bottom region of the tank. Okay? Any questions? Any questions?
None, Miss.
I'm supposed to discuss hydrostatic pressure, still part of the worded problems actually, and then we'll have multiple integration. Multiple integration is just requiring you to do integration twice, not just once or thrice, depending on the number of integral signs that you see. So it's kind of, if we're not going to talk about its application, it's just kind of procedural, because we have devoted our midterm section entirely on the techniques of integration. So if you see 2 integral signs, then you just have to integrate twice. But of course, what you're going to integrate is the answer to the first integration. So it's all about procedure. If we have time next meeting class, I will discuss first a little on hydrostatic pressure, but still will confer with the other teachers if it will be included. If not, we'll go straight to multiple integrals. Your quiz then will just be the 3 quizzes for NTEM. There won't be any quiz on this topic, but of course the topics that I'll be discussing will still be included in your NTEM exam. Okay? Now,